Hello subscribers, welcome to Stamatics tutorial. Here we are going to discuss addition theorem of expectation for n events. Those who are watching a video for a first time, please subscribe, like and share the video.
Addition theorem of expectation for n events. Statement: if x1, x2, so on xn are continuous random variables, then prove that expectation of x1 plus x2 plus so on xn equal to expectation of x1 plus expectation of x2 plus so on expectation of xn. So, this theorem we are going to prove by using mathematical induction. So, before going to the proof, let us write in proof. First we will write what is the formula for expectation of x, because if you know that formula only you can solve the theorem. So, let us write that formula. We have expectation of x equal to integral x equal to minus infinity to plus infinity x into f of x dx. So this is the formula for expectation of x. Now we prove this theorem by using mathematical induction. So in mathematical induction, case 1, we will prove that the theorem is true for n equal to 2 events. In case 2, we will assume that the theorem is true for n equal to k events. And in case 3, we will directly prove that the theorem is true for n equal to k plus 1 events, so that our proof is done. So now let us go for case 1. Case 1. So let us assume this statement equation as star. Let us assume this equation as star. Expectation of x1, x2, so on xn equal to expectation of x1 plus expectation of x2 plus so on expectation of xn. So let us assume that equation as star. Now case 1, we prove that what we are going to do in case 1, we are going to prove that the equation star is true for n equal to 2 events. N equal to 2 events. So here the 2 events means 2 random variables. As we are in addition theorem, so we are going to add that expectation of x1 plus x2 equal to. Now by using this expectation formula, we are going to write the formula for expectation of x1 plus x2. In expectation of x, we have only one random variable, so we have written integration x equal to minus infinity to plus infinity. Now here we are having 2 independent random variables, so we will take the integration with respect to 2 variables x1 and x2. Integral x1 equal to minus infinity to plus infinity. Integral x2 equal to minus infinity to plus infinity. So in place of x, we are having now x1 plus x2. Take down in a bracket x1 plus x2 into f of here only one variable we are having, so we have written x. Here 2 variables are there, so f of function is with respect to 2 variable, f of x1 comma x2 and into dx1 dx2, as 2 integration is with respect to 2 variables. Now this you have to multiply x1 into f of x1 comma x2 dx1 plus double integrals x2 into f of x1 plus x1 comma x2 into dx2. Let us do that. So integral x1 equal to minus infinity to plus infinity, integral x2 equal to minus infinity to plus infinity, x1 into f of x1 comma x2 dx1 dx2 plus again double integrals x1 equal to minus infinity to plus infinity, x2 equal to minus infinity to plus infinity, x2 into f of x1 comma x2 into dx1 dx2. So now next step, see here in this first term, so integration is with respect to x1 and x2. Let us frame according to that. So integral x1 equal to minus infinity to plus infinity. So we will write here x1 into dx2 we will get a, but let us start bracket here. Integral x2 equal to minus infinity to plus infinity. So here we are having x1 and x2. You can write here f of x1 comma x2 into dx2, because the integration is with respect to x2. Now we'll close the bracket into dx1, because in integration, first we have to integrate with respect to x2. Once it is done, then x1 term will come. After getting the answer, you can integrate it with respect to x1. So this is the process. Similarly, in the second term also, we will do like that only. So here we have x2 as a first term into f of x1 comma x2. So here x1 only one term is there, that too in f of x1. So we will write first x2 integration x2 equal to minus infinity to plus infinity. x2 we will write brackets open, integral x1 equal to minus infinity to plus infinity f of x1 comma x2 into dx1, because integration is with respect to dx1. Once it is done, we will integrate it with respect to x2. So this is the process. Next, so integral x1 equal to minus infinity to plus infinity x1 into, so now the integration of this term becomes what? This term becomes f of x1, because here we are integrating it with respect to x2. So obviously we will be having x1. So f of x1 into dx1. We have the bracketed term answer is f of x1 into dx1. Plus similarly here also integration x2 equal to minus infinity to plus infinity x2 as it is. And here the bracketed term integration of f of x1 comma x2 with respect to x1 is f of x2. So f of x2 into dx2. Now, this represents what? This equation represents what? x1 integral of x1 into f of x1 dx1. This is expectation of x1 because we have here expectation of x equal to integral x into f of x dx. So if you can compare this two, in place of x we are having x1 and in the second term in place of x we are having x2. So let us substitute directly. Therefore, expectation of x1 plus x2 equal to expectation of x1 plus expectation of x2. Hence, let us assume this as equation 1. Therefore, equation star is true for n equal to 2 events. N equal to 2 events. Next, case 2. So case 2, assume that the theorem is what I told, for n equal to k events we are going to prove. Assume that equation star is true for n equal to k events. We are just assuming, that's it. So we are not proving here, directly we can write, say expectation of, 1 minute. So as we are having here n events, we got the statement as expectation of x1 plus x2 plus so on xn equal to expectation of x1 plus expectation of x2 plus so on expectation of xn. So if we are having k events, then the formula changes to expectation of x1 plus x2 plus so on xk equal to expectation of x1 plus expectation of x2 plus so on expectation of xk. So in case 2, now we are going to get the same thing. As we are having k events, so we will be getting expectation of x1 plus x2 plus so on expectation of xk equal to expectation of x1 plus expectation of x2 plus so on plus expectation of xk. Assume this as equation 2. Now 2 cases are done. Now the third case. Finally we are in third case. So what we have to do? We have to prove that, equation star is true for n equal to k plus 1 events. So how many events will be having here? K plus 1 events. That means k random variables we will be having here. So expectation of x1 plus, we will be having k plus 1 events. So random variables also will be having k plus 1 random variables. So here I am writing expectation of x1 plus x2 plus so on xk plus xk plus 1. So now how to solve this? So here from equation 1, expectation of x1 plus x2 equal to expectation of x1 plus expectation of x2. Same way, let us assume this has two events, x1, x2. So expectation of x1 plus x2 is expectation of x1 plus expectation of x2. So now expectation of x1 is, this whole term is expectation of x1 plus x2 plus so on xk plus x1 is done. Now expectation of x2, in place of x2 we have only xk. So expectation of xk, since from equation 1 we have split this one by using equation 1. Next, what is this? From this is what? This is exactly the equation 2. So expectation of x1 plus x2 plus so on xk can be written as expectation of x1 plus expectation of x2 plus expectation of xk. Directly you can substitute. So equal to expectation of x1 plus expectation of x2 plus so on expectation of xk. This is done here, k plus 1, sorry. So expectation of xk plus 1. From where you have written this? Since from using, or else substitute equation 2 you can write here. Substitute equation 2. Now this is done. So you can see on the left hand side, expectation of x1 plus x2 plus so on xk plus xk plus 1. Here you are having k plus 1 events, and here also you got k plus 1 events. Therefore, hence the theorem is proved. Till here you can by this the theorem is completed. But if you want the exact statement to be proved here, you can just replace k plus 1 with n. Directly, once you are done with the step, you can write directly here expectation of, substitute k plus 1 equal to n. So our theorem becomes x1 plus x2 plus so on xn equal to expectation of x1 plus so on expectation of xk plus expectation of xn. So you can do in that way also.